Okay, it's recording.
I can share. I think you have to tell me the host. Okay. Okay, can you guys see my screen?
Yeah, perfectly fine.
Okay. So again, just going through lecture 3 and 4 is mostly about not embedding and Pagerank. As a reminder, last week we had an introduction for why we need machine learning with graphs, some applications, use cases, like the different tasks that we have for node, edge, and graph level, and ways of representing the graph, and most of the old school how to do machine learning by extracting hand features for node level, link level, and graph level. So today is more like a machine learning approach, how to use not embeddings for to the not task level, which are mostly unsupervised, or to embed also like graphs. So in that sense, let's start. Let's go through like, and also like guys, there's, I know like today we're like a small crowd, like, but any of you want to, if you want to talk about any specific section, just let me know. Or like you guys want to go faster and we make it like as a discussion, I think that would be like much better. But let's go through the slides so far until we find like a way of managing the reading group. So for today, like we have like again like the old pipeline. Like first we had to learn the kind features, but this time instead of learning this kind features, we had like the representation learning boom, where like these features are learned automatically. And how do we do this in graphs? So basically, like to have like to learn a function where we can map a node to some vector space. So these ones are called embeddings, and these embeddings we can use. These are based like in a similarity function. This is how we define similarity for embeddings. So, and these we can use for different tasks, such as not.
Javier, are you scrolling on your screen or something? Because I do
Oh
not
yeah,
see movement.
it's not moving.
I do not see it. I'm still seeing like the first page of the PageRank lecture.
Here it says.
Yeah, me too.
Oh, okay, let me just share again. I am in slide number 5.
Yeah, now I can see it.
I'm moving though.
Yeah.
Yes.
Okay. All right, so let's continue. So first I was saying, okay, we kind of reuse these node embeddings, and basically we can map from a graph, which is a that structure where it's like super sparse, to high dimensional space. So here, like we plot the cloud network, and we can say that actually there is a notion of similarity, and these embeddings are capturing like some notion of similarity. So now let's see like how this works and how do we define this with an encoder-decoder model. So first for the setup, we have, as in most cases for graphs, we have the adjacency matrix and vertices, which is the graph. And in this case, we like for now we don't use not features or edge features, and the goal is to encode nodes in an embedding space, such that when we have like a dot product or we apply any similarity function, we can define a concept of similarity in this space. And this space is often like is like a small space where we can play with. So a D-dimensional space. So okay. So everything like the main part like for this encoder decoder model basically is like how to define the similarity function and how to define this notion of similarity. So the idea is like that an encoder is just gonna take given a node is gonna take that embedding for such node. So if I say like encoder of node U is gonna give me the embedding for node U. And we use a similarity function to measure like similarity of a node. In this case, it could be like different things. And I think that's like a big part of research because like if I work in social networks, like I want like to have like my closest friends. So that's my notion of similarity. But if I'm working, I don't know, another task where I care more about like the 4 nodes, we have to define like a different notion of similarity. And the decoder basically, the goal of the decoder is to take to map from the embedding to the similarity score. So define like how similar a node it is. So given an embedding from node B and an embedding from node U, how close are these to each other? And basically we optimize on this such that given these 2 nodes, this has to be true. So this has to be similar. So here the key part is like, okay, how do we get like this encoder function and how to define the similarity function? The basic idea is just like have like the dot product. So which will be like the cosine similarity between node B and node U, given it's embedded. So the most simple approach for the encoder, it will be first just having like this shallow encoder, where we represent like a matrix Z, where each column is a node embedding. So it's what we want to learn. So, and also we have a B vector where we have is an indicator vector. We have a 1. So every time that a node appears for that node. So in that case, it's just like doing a lookup in this Z matrix. So like if we have a B, that basically we select that column or that node for that specific case. And this is basically the essential idea for algorithms such as deep work and not together. So far we have the encoder and decoder framework. We have a shallow encoder, which it could be seen just as an embedding lookup. Z is going to be your matrix that we want to learn. And the objective will be like to make nodes that are close to each other similar. So we want to maximize that. So there is still a lot of questions that here, but how do we? What is similarity? Right now, like for us, like just optimizing ZU and ZV. But how we define this notion of similarity? There are different ways, as I said, like we can say like just when they are linked, when they share neighborhoods, structural roles. But we're going to start like with something that's called random walks. Next. So far, like we defined this notion of embeddings. The good thing about this is that it's unsupervised. So we just have an encoder-decoder model. When in the encoder, we just select an embedding, and in the decoder, we match this embedding with a similarity score. And all of this is unsupervised, and the similarity score we define it. So we have the sense, like we have a sense of notion to define this similarity. And this is unsupervised, which is good. But the thing is, like for now, we don't use not features, which might be important. Like we want to encode like different information, or we want to add like prior knowledge. And the good thing also is that we can use these embeddings to other tasks. So we can do like you're reusing the embeddings for classification or downstream tasks. So now we get into random walk approaches for non-embeddings. So far, so good. Take that as a yes. Right. So for now, we have a notion like a vector, a probability, where like we want to predict the probability of visiting node B on a random walk starting at node U. We have two functions, softmax and sigmoid. So they both try to get like probabilities. And we have this notion of random walk. So what is a random walk? So random walk is just like a sequence of points where we start on a given node and we move in a fixed length randomly in the graph. So the points that were visited during this random walk is my sequence for my random walk. So this is gonna be my notion of similarity. So it's like how I'm gonna select neighbors based on in a stochastic approach. And this comes like from a notion of word to vect. So basically they're trying to imitate the same two graphs. So we can think of the sequence as a sentence for the graph where nodes that appear together, they are similar to each other. Such that every time like if U and B are close to each other, we're gonna have a high probability. If not, it's gonna be a low probability. Okay, so now going to random walk embeddings. So that would be the goal, to find this ZU and this ZB to define a notion of similarity. So on one side, we're gonna have this random walk strategy. And on the other side, to optimize the embeddings to encode these random walks. For now, it's just gonna be dot product. So why random walks is because one is they are expressible. Like we can say like this is stochastic approach. It actually works because I'm looking and my neighbors are close to each other. That would be like a local information, and I can have like random walks of length k, where I can reach to really high order neighborhoods. And this is efficient. Yes and no, I'd say, but this is efficient because we don't need to consider all knot pairs in training. Okay. So again, we are in this world of unsupervised feature learning. The goal is to find the embedding of nodes of d-dimensional space. And the idea is like, how do we want to define the similarity? Is that nearby nodes are close to each other. So we want to define a random walk or a neighborhood based on a random walk strategy R. So we can think of this like as a feature learning problem where we frame this problem as an optimization problem. So now we were given a graph and our goal is to learn this mapping function. So this mapping function is just gonna take a node and it's gonna return me like an embedding. And we use here like an approach of doing like maximum log likelihood, where we say, okay, I want to maximize the probability of this sequence for this neighborhood given like an embedding. So in general, like this is from the original paper, like from the walk, they use like a short fixed length for random walks. And the neighborhood, it would be like a multi-set. And we optimize based on this. So it will be just using maximum likelihood object, where this probability is just a softmax. It's just how we get like probabilities. But what happens that in reality, this is complex. This exponential part we have to add over all nodes. So this is like it has a big O, a complexity of the number of nodes in the graph square. So it's if we have like a large graph, that's a lot. So just to go over that, in this paper, they use negative sampling. So negative sampling, basically, you just take k random negative samples from a random distribution, from a noise distribution, and you do the same. So here it would be like the probability of having a 0 or 1. Now we replace this with a sigmoid instead of a softmax, because this is now binary. And we do the same over the negative samplings, where we penalize. That's why we have this negative. And here, like, two considerations that I think these two are important, because this is for specific for the algorithm to make it work. One is that higher, like a higher k gives more robust estimates, and a higher k corresponds to higher bias on negative samples. And this makes sense because it's as you were doing like the whole normalization. So the higher it is, the more you're adding like a penalization. So then again, like they got a little bit of the stochastic gradient descent. So this will be the same, it's nothing new. Okay, so here the important part is basically this is an algorithm called deep walk, where they run like short fixed length random walks in the graph. So that would be like the strategy to collect this neighborhood. And they optimize this using stochastic gradient descent, doing maximum log likelihood, and using negative sampling. So that's basically deep walk. And that's how they generate the first plot that we saw from the Sakari network. So yeah, so the idea is now like how we can generalize this. So this is strategy, like just sampling random walks of fixed length, is naive, we can say, and is the simplest idea. So this is the walk. So now we can generalize this. So then it comes like this algorithm is called not to beg, where they say, okay, instead of doing just like a random walk, we can use, or we can develop a second order random walk as the strategy to sample random walks. So the main idea here is like, how do we, what is this second order random walk? So here it is. So on one side, they say, okay, let's take this local and global view of the network. How do we take advantage of that? Because random walk, what it's saying, it could be both, right? Because it's random. So we can go like to really like long paths as we can stay in the closed neighborhood. So it could be local and global, but we don't have any control over that in deep work. So they say, okay, let's take advantage because if we assume like a breadth first search, we can assume that since we're going always like from level to for each node, this is a local view of the graph. And that first search, since we're going like over the levels, this could be seen as a global view of the graph. So they define this bias, this notion of bias walks, where they say, okay, when you do like if I start a node U and I do like a breadth first search, I'm getting only, and if I have a walk of length 3, I'm getting nodes S1, S3, and S2, which is my local neighborhood. And if I want to have like a global neighborhood, I can do like a depth first search, where I'm gonna go straight like from U to S4 to S5 and S6. So I will the definition of why using this notion of having the local and global view. So now we have some control for our strategy for doing random walks. So, but like, how do we train this? So there's an interpolation on how do we choose on selecting global or local walks. So again, we come back to this notion of second order random walks. And we could define these parameters. So there's a P parameter and a Q parameter. So the P parameter basically is going to say the probability that if I had to go to if I had to return to the previous node. And the Q parameter is an in or out parameter. What it says like, I want to go to stay in my local neighborhood or go to the global neighborhood. So it will be like, I want to do deep first search or breadth first search. And basically it's just the ratio. So as an example, if I just traverse from S1 to SW and now I am an SW, so the idea also like why is second order random walk is because I always remember the previous, the first order will be like going from S1 to W. So that will be like, that's what this is called the same distance to S1. And now like if I have like, if I am in W, I have three options in this case for a walk of length 1. I can go back to S1, or I can go to S2, which has the same distance to S1, or I can go to a further node from S1, which is this one. So here it will be only 1, because I have to move only 1. And here it will be like 2, because I have to go 1 and 2. So this one is far. So there is now this is strategy. How do we build this? And let's say we have like 2. Yeah, you want to say something for it?
So I have a question.
Yeah.
From W, why is the probability to S to 1? It should also be 1 over 2, right?
Why is here? Oh, sorry. Here. Why is here like 1 and not 1 over P?
Or it should be 1 over Q because it's not going back to the same.
Oh, no.
node.
Okay. This is what I understand, but correct me when I'm wrong. Okay. So 1 over, you said like it will be here like 1 over Q, but it's not because it's just measuring the probability of the visited nodes. So the probability from here to here is 1 over P, because this was my first order random walk. So this is what I remember for now. So that's why it's 1 over P. It's just the probability of going back to the same node. But now like going back from, like now in W, I have only one option, an S2. And this is probability 1 because this one has the same distance as going back to S1. So this distance is the same. This is 1. So this will be like doing going back to S1, but to a different path. So this distance is the same. So that's why it's this one.
Okay.
But like, since I was in this node in S1 and going to W, to go to S3, like in my first order will be like S1 to W, and my second order will be like either W to S2, W to S3, W to S4, and W to S1 are my possibilities in the second order.
So if there is like no edge between S1 and S2, then the probability of going to S2 would be 1 over Q.
Yeah.
Right.
Yeah.
Okay.
Just because this distance is the same.
Okay.
So yeah, and then yeah, and then we can define like 1 over Q also, which will be like either we explore or we come back. So it will be basically what we can control in this bias band work. So Q is like how much I want to Q is how much I want to explore either in the local or global neighborhood. And P will be like if I want to stay in the same neighborhood, if I have to go back. And basically you can then define this transition probability, which will be the matrix. But I just like understand like how do you compute this random, like number 1, I don't know how to do it. It will be just these probabilities because I think this one, it was just as an example.
Yeah, I think it will be normalized probabilities multiplied over each time step. So the
Okay, so
probability that the list above is just for the first time step, and then they normalize it, and then they obtain the probability for the next time step, and so on.
okay, so you do this several times, and that will be like the random walk probabilities.
Yeah, depending on the fixed length that you want to work with. If
Yeah,
the
yeah,
fixed
okay.
length is 3, then you just do it for 3 time steps, I think.
Yeah, yeah, okay, that makes sense now. So okay, then we have this, and now it makes sense that we have that length, and then we just do not to vect with that. Now we have that probability where we can optimize, and we have not embedded. So that would be it, like not to vect. So remember, it's basically the same idea of P. We just have to define a different strategy, and for doing that, to control local and global neighborhood, and exploration and exploitation, we use P and Q. That would be it. We have different also notions of this, like how to do these random walk strategies. And it was super popular, I think, between 2015 and 2018, before the GCN. So this paper, I think, is popular if you guys want to review. And this is one of the popular papers now from Giant Tank. But and so far, so good. Everything's still, everyone's still on track. And I go a little bit faster because we have to cover lecture 2. I take it too long, I think. Okay, now we're like now we have like okay this notion of embeddings, but now it's like we go forward. Like we have not embeddings, but we want also to embed the entire graph. And this can be used like for different from different tasks, or such as here like classifying toxic versus non-toxic molecules and doing anomalous and detection in graphs. So the idea that the simplest one is just like to take like the embeddings, like the ones that we saw, the not embeddings from any task, and just do average or a sum. So that would be my graph embedding. The second approach would be like just when we train these not embeddings, we incorporate this notion of having a virtual node. So it would be like in papers of like in when we do like a document embedding or something like that, we do word embeddings where we also add a document embedding. So it would be the same notion, the same idea. So here we have this virtual node which captures the global the, the global similarity between a graph, and that would be our embedding space. And this one, which is what it wasn't like super clear for me, but I tried to explain. And we have this third approach, which is anonymous walk embeddings, where we define a random walk. And an anonymous walk, it is called anonymous because we basically ignore everything that comes after, but we define if a random walk is the same to other random walk if we start if both random walks correspond to the same index the first time that was visited to that node. Okay, that was too complicated. It's like if we have two random walks like this, they are the same length, and independent of what happens next, if they both started at the same node, uh, it is basically the same anonymous walk. So that's what I understand from an anonymous walk. Okay. Then it's like, so that's just an example. And the thing is like also these anonymous walks, they grow exponentially. So based on the number of walks that I'm taking, so in this case, if I'm taking anonymous walks of length 3, these are all the combinations. But as I increase the length, I have more and more combinations, and this can grow like super high with a small length. I'll just try. So here we can say like just for a length of number 3, we have five combinations.
So I was curious if like there is a straightforward formula for getting the number of anonymous walks for given length, but I'm not sure. Is there?
Yeah, I don't know either. I don't know actually how to generate this because you can end up in the same.
Yeah.
Yeah.
Yeah, it's not a factorial, so I don't know what it is.
No, yeah. And so here is like how do we learn then the graph embedding? Basically, they just take like the based on the number of anonymous random walks that we take from that given length. For example, here like the length is going to be 3. The embedding is going to be of number 5. This is going to represent only the counts. So that's going to be the probability for that graph. So this is basically how to represent that probability. And this is M. And also how do you compute the, well, I don't remember what was this. Anybody remember what was this? How many random walks and doing in case somebody is coming also. Okay, I don't remember this. But the next thing is like, how do we learn these random walks now using embeddings? And the idea, basically the concept is the same. It's just that now we use embeddings and the objective function changes. So here, instead of just doing this part, where we know only this probability, the probability here now is using embeddings, where we define like different lengths in a window size. And then we add over all of these, all the values in this window, and that basically will be the random walk. And it's super explanatory here. So here we have the graph. We generate like a bunch of anonymous random walks. We embed those values. We concatenate of average them, and we try to predict the next step for that random walk of that length. And basically, we optimize this. We should learn this graph embed. So that would be it. So we have like so far 3 approaches for learning, like embedding graphs. One will be just averaging and concatenating node embeddings. The other one will be just having a virtual node. And the tier 1 just doing anonymous walk embeddings. I never heard of that before. That was something new for me. It was difficult to grasp. So for random walks, we can just have the based on occurrence or use embeddings. And then we'll see later like these hierarchical embeddings. And now how we use these embeddings. We can use these embeddings for basic clustering, node classification, link prediction, graph classification. And that was it. Do you guys have any questions so far? We have 15 minutes for the next lecture. I don't know how far we can go today. Sorry, it took too long. But I hope everything's clear though. Take that as a yes. And blessing is here. A welcome blessing. Victor, you can go, I think, to the
Thank you.
questions.
Okay, so if there are no questions to that, then I will try to share my screen and go through the Pagerank lecture. So just stop sharing the screen and, oh, you need to give me back the host. I will add that in the meeting settings next time. Okay. Okay, so can you see the screen?
Yep.
Okay. So this lecture is basically about Pagerank, the connection to random walks and other kinds of embeddings. So the basic idea is to estimate the importance of nodes using, for example, random walks. And this is what Pagerank is about. And Pagerank is the algorithm that was initially used by Google to show the search results. And what we can see that node embeddings can be also written as matrix factorization, also deep walk and node to vec. Everything.
Is it just me again, or Peter's voice was like it's super low?
I will check it again. Yeah, it also reset it. So is it okay now?
Yes, it's not okay now.
Okay. Okay, so I would try to go quickly because there are many examples, but it's not that important right here. So the example started with the motivation for this algorithm. So to represent the whole web as a graph, so where you can hear me again. I don't know what is going wrong with my mic today, but I will monitor it. So please let me know in the chat if it resets again. Okay. Yeah, where the graph was built like web pages. I don't know. So web pages were nodes. I don't know what is really wrong with the mic today. And I don't know why it keeps moving back to low, but if it doesn't help, I will just give the presentation back to Javier. Is it okay right now?
Yeah, it is okay.
Okay, so maybe let's try this. And all edges in the graph were defined just by the hyperlinks on the web pages, so that if you reference another page, you get a directed edge to that other web page. And there are examples. We are not really interested in that right now. And yeah, so if you have, for example, that kind of graph, then the question is, should, for example, a node like this blue one and the red one have the same importance? And if you just build a graph like that and do nothing else, then they will have the same importance, but that's not really how it should be. And PageRank, personalized PageRank and random walks with restarts should be a tool to fix the importance and calculate it properly. Okay, so the first idea would be to take the in degree of the nodes and see if that helps. So for example, for the Stanford webpage, it would have about 20,000 in links, so other web pages that reference Stanford. And the other page, like this person do not exist.com, has only one other page that references it. So Stanford should be assigned a much higher importance. Okay, so in this example, we saw that, for example, node I has 3 outgoing edges to other web pages, so its importance should be split equal to all the 3 pages. And we define it like that for all the pages. And then we say, if we want to compute the importance for a node, let's say J, then we look at all the incoming edges, and we have the incoming edge from page I and from page K, but all renormalized, we could say, by the factor of the out degrees of those nodes, and we just sum it together. But in such a notion, we see that it is defined recursively. So how we should compute it? We built a so-called stochastic adjacency matrix M, where all columns have values of 1 over the degree. So the whole column sums up to 1. And then we define a rank vector, so that's what we're interested in. And this rank vector should sum up to 1, as we defined previously. And then the whole objective that we want to capture is that the rank vector should be the stochastic adjacency matrix times the rank vector. So you should immediately see that this is related to the eigenvector centrality that we discussed last week. And yeah, then some other examples. And another view for this kind of importance, you could say, is by random walking. So we say that at a given time t, a surfer is on some web page I, and he moves to another page at time t+1, for example, uniformly at random, following all the outgoing links on that page. And we want to define probabilities that a surfer is on a ith web page during time t. And then we also see that this is related to the same equation that we saw previously. So when being at time t, we have such probability, then we multiply it by the matrix M, and we get the new probabilities. But if we assume that after some time this distribution becomes stationary, then we have an equation like that, which is basically the same thing as the one R equals M times R. Yeah, and as I mentioned, it is just the eigenvector problem here. So we want to estimate this eigenvector C for a given eigenvalue. And we could do that, for example, this flow equation by assuming that the constant is equal to 1. So we want the eigenvector for the eigenvalue equal 1. And, and how can we solve that is by using the power iteration method, which does something like this. So you just get with some initial PageRank values, and then until convergence, you just recompute the values of the rank vectors. So you just multiply it every time by the matrix M. And you do it as long as the values don't stop to change, like above a certain threshold epsilon. And it was shown that about 50 iterations is sufficient to get decent results. And yeah, another example. Okay, then there were some questions like, does this even converge to, does it converge to what we want? And are these results reasonable? So there were two problems with this formulation of the problem. For first, dead ends, so nodes that have no outgoing links, and spider traps, so nodes that have, for example, multiple incoming edges, but there's only a self loop, so the random walking or the flow just gets trapped in that one node, and eventually this one node or web page receives the whole importance over the whole graph. So yeah, that's what basically is shown here. So we start out with any given importance assignment, but after a certain number of steps, this node with the self loop receives all the importance. And that end means that after a certain number of iterations, all the importance is gone. So the problem is not well defined in this setting. And what can we do for spider traps is to either continue the random walk or to jump at a random page uniformly over the whole graph. And here we define a value beta, which says either you follow the link with such probability, or with 1 minus beta, you jump to another random node or random page. And that will help with the spider traps. For dead ends, if you go to a dead end, then with probability 1, you just teleport to another random node. And that should fix all the problems. Yeah, that's what we discussed. And the final equation would be for this Pagerank equation. So either with value beta, you go to the next links, or with 1 minus beta, you teleport randomly to 1 out of n nodes. Yeah, and that's exactly what Google used in its initial days. Also, you can solve it with the power iteration method. And again, an example. Okay. So the motivating example for the next methods, like the personalized PageRank and random walks with restarts, is here given by a recommendation example. So given a set of users and a set of items, you want to find the best items for a given user that he did not buy yet. And you define a proximity on graphs for that. And now you have to decide how to decide which is more related. For example, A and A prime, or B prime. And you could do that by using just shortest paths, and see that, for example, in this case, A and A prime have the shorter path than B and B prime, because you need to go through another additional item here. But also you need to think about the common neighbors of such setting. Okay. So in the traditional PageRank, we saw how it works. So you just teleport uniformly with a uniform probability to any node in the network. For personalized PageRank, you take a subset of nodes you can teleport to. And in the example of random walks with restarts, this set contains only one node, namely the starting node. Okay. I didn't really get the example right here, so if anyone has a comment to this section, then I would highly appreciate that. But if not, we will just move forward.
Yeah, I think as far as I understand, in this case, they're just trying to do a random, like if you're talking about the code that they have, the pseudocode that they have in here, they're just trying to actually do the random walk by finding a random neighbor and jumping to that position. And it's like sampling a certain other nodes which are at a certain distance, which are at a short distance from the query node, kind of.
Okay.
Does that make sense?
Yeah, that makes sense. Yeah, and that also like goes the same idea like I talked before. So in PageRank, you assign the restart, the set you can go when teleporting is just the same probability uniformly assigned to all nodes. In personalized PageRank, which was also called topic-specific PageRank, it's only certain nodes or a subset of nodes. And with random walk with restarts, you just choose one node. And that was it for this section. And the last part in this lecture was about connecting node embeddings to matrix factorization. So again, we defined that node embeddings for now are just encoded using shallow encoders, so a lookup table. And what we want to do, for example, is say that if the similarity of the embeddings defined by the dot product could be equal to the adjacency matrix, so if there is an edge between a pair of nodes, then the dot product should be the highest one, and otherwise it should be 0. And maybe we could define it like that, but there is a problem with the dimensionality of both matrices, so it's not feasible to learn that. But we could just define an objective as minimizing the Frobenius norm between the adjacency matrix and the dot product of the embedding matrix. And this could be seen as a matrix factorization version of the node embedding, so the matrix factorization of the adjacency matrix. And in the paper reference in this lecture, the authors showed that both deep walk line, node2vec, and PTE can be rewritten instead of performing actual random walks, just to rewrite them as matrix factorization problems. And for example, for deep walk or node2vec, the equation looks like that. So we take the adjacency matrix, normalize it by the degree matrix, then we sum over all context window sizes, and renormalize it, then look how many edges are there in the graph, so compute the volume of the graph, and then add the number of negative samples, again renormalize it, and take the logarithm of everything. For node2vec, it will be a bit more complicated, but it's if you were interested, just look up the paper. Maybe we can also discuss it in some other meeting. And the limitations of the shallow embeddings, like we call them, is first of all, it's a purely transductive case. So if you have an update in your graph and some new nodes occur, then you have no way to estimate the embedding for it other than just recomputing the whole thing from scratch. There were some papers about it, how you can maybe use the existing information to compute a new node embedding, but nowadays you just use some inductive methods like graph neural networks, and then you can just infer for unseen examples. And the second limitation for the methods defined here is that you cannot really capture the structural similarity. So in this example right here, node 1, 2, and 3 should have representations that are similar to 11, 12, and 13, but due to the fact that we use random walks or the maps that are related to random walks, the distance between those nodes is quite high, so they will receive completely different embeddings. So deep walk and node2vec cannot capture really structural similarity. And the most obvious limitation, which was introduced at the beginning, is that we do not utilize any kind of features like node, edge, or graph features. And for the solution is just use deep representation learning and graph neural networks, which will be discussed during the next meeting. And yeah, that should be everything, I guess. So any additional questions or something you would like to discuss?
No. I guess that's enough.
I was,
Okay.
sorry, Javi, go ahead.
No, you go ahead.
I was just thinking that maybe next time we should do just one lecture instead of two and leave like the other half hour to discuss a paper.
Yeah, or we can go faster, like because I expect like everyone went through the lectures.
Yeah.
So
yeah, we can go faster.
yeah, we can just discuss like is there like any specific point where we can discuss, because for next week we have PPR go online that I think are two interesting papers for PageRank and also like not embeddings. So we can take one of those and just go through. Next week it will be label propagation for not classification and GNNs. So the idea is like to go faster, but I remember like some people were also like concerned like about like hands-on experience. There is the collab and with the course, and also the homeworks, but I haven't find the homework assignments. If somebody finds them on the homeworks for the course, just send it in the chat.
So
But
they have the collab homeworks out, which is like the programming assignments, I think. So
okay.
those we can access.
Yeah,
Okay.
and
But
there
like
it's
the
solved
first one
actually.
was kind of straightforward.
Yeah. So yeah, I went to this and the first one and second collab. They are super like self-explanatory, but I think the next one is just like it covers a little bit with the open benchmark, the framework that they have for the data set and Python geometric. So we can just go over a little bit if you guys want to go. So we can cover a little bit also like how do we actually do this in practice. But yeah, there's a lot of things to do. It depends on like how you guys like how do we take shape. Like this is only the second session, but I think yeah, lectures should be less because it becomes even boring. I don't know you guys, but like I don't want.
Yeah,
I
I
don't
think I
want.
agree with you.
Yeah, I don't know. I don't want like either Peter or me are the only person talking. This is like a discussion group, so let's try to make it like interactive and a discussion. And I think more people will join like little by little, hopefully. Yeah. So let's see like that for next week and send the message. We can cover the next two lectures. We'll go faster. Let's try to cover like for the first half an hour, just the lectures and see like if there's any discussion. And then, but if you guys want to go to prepare go online, if you have any other paper also from the slides or you want to share that is from the topics that we've been talking, and we can discuss also that paper and we can vote. I send that in the chat. And about the collab, we can cover also next week. We can take just a 10 minutes to cover the collab. The
Yeah,
collab.
that's a good idea.
Yeah, we can just run and execute, and somebody has a question about the code or how do we do, we can just cover that because I think it's much easier if you guys play with it. That's how you learn. So yeah, anything else that you have any feedback, anything that you would like to change? I went like over, like I think I didn't leave in space for Peter. Sorry about that. But yeah, if you have guys any feedback, anything, just let us know in the chat later. Yeah, and thank you for everyone for joining. Do you have anything to add there?
No, that's basically it. So I also thank you, everyone.
Yeah, and thank you everyone for joining. I appreciate it.
Thanks, Peter and Javi. Bye.
All right. Have a good week.
Bye guys.
Bye, guys. Take care.